Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the last video we added a brand new input module to our game engine and today we are going to use it to move the camera around the scene. First we are going to make it possible for entity scripts to receive events from the input system, and then we are going to write a bit of script code that will move the camera around depending on the user input. In order for the entity script to be able to subscribe to input events, we need to write an input system class that inherits from the input system base class. If we make this a template class, we can make it aware of the type of entity scripts so that we can register member function pointers as event handlers. Function pointers that point to member functions are a bit more complicated than function pointers to free functions. For member functions, we actually need two pointers. One that points to the class instance and another one that points to the member function. We can define the event handler's signature that will be called back when an input event is raised. The instance pointer together with this signature form an input callback. And then we can have an array of event handlers or input callbacks. Note that we have a different array for each input type, so that keyboard, mouse and other input devices all have their own array of input callbacks. Now let's have a look at how this can work in practice. First, I'll create a new script that we can attach to the camera. We want to use the input system to move the camera around. We create an instance of the input system as a member variable in order to receive input events. Note that the template argument is the camera script class. In order to use this class, we need to implement the onEvent virtual function from the base class. This function calls all event handlers in the array that correspond to the input type. To add an event handler, we need to have a function that takes the input type for which we want to get called back, the instance pointer and the member function pointer. Then it looks in the array of callbacks for this input type to see if it can find an entry with the same instance pointer and callback function. If it finds such an entry, that means that the event handler is already registered and it returns. If not, it will add a new input callback to the collection of input handlers. Now we can go back to our camera script and write an event handler function for mouse movement. We can add this event handler in the script's constructor. This is all we need to do in the entity script to get called back for mouse events. Pretty simple, isn't it? Need to fix a typo here first, and if we set a breakpoint in our function, we should see that it will be hit. I don't know if it would break in an empty function, so let's add an actual line of code here. It's still not calling the function, but it does seem to raise the event. Oh, of course. I forgot to actually attach the camera script to our cameras. And there you go. Our mouse event handler is getting called when I move the mouse. Okay, well, let's use the mouse to rotate the camera so that we can look around the scene. To do so, we take the camera's orientation and convert that to spherical coordinates. But first, let me use our own F32 type instead of float. So I need to change these to F32. Okay, back to spherical coordinates. In case that you are not already familiar with this, it's a way of describing a point on the surface of a sphere using only two numbers. The first number is theta, which is the angle that a vector from the origin to that point makes with the pole of the sphere and has a range between 0 and pi. The second parameter is phi, which is the angle with respect to the positive x-axis. Phi has a range between 0 and 2 pi. We can convert any Cartesian coordinate that is on the surface of the sphere to spherical coordinates using these equations. And we can convert spherical coordinates to Cartesian coordinates using these equations. Remember that theta and phi are with respect to the sphere's up-axis and the positive x-axis respectively. However, the orientation of objects in primal engine is with respect to the positive z-axis. In other words, the front vector of objects in primal engine is pointing towards the positive z-axis. So we need to subtract half of pi from theta and add half of pi to phi. Let me define a constant for half pi as well. Now we can remember the orientation of the camera in spherical coordinates by putting it in a member variable. Then in the mouse event handler, if the mouse position was changed and the left mouse button is pressed, we will change the camera's orientation by the amount of mouse movement. We can check if the mouse left button was pressed by simply asking the input for its current state. Next, we calculate how much the mouse was moved in x and y directions by subtracting the current and previous values of its position. I'm scaling these with some arbitrary value that we need to fine-tune later on. You can view this as the mouse sensitivity function in game settings. We then change the camera direction in spherical coordinates by an amount proportional to how much the mouse was moved. Note that the x and y directions are switched because moving the mouse horizontally or in the x direction results in a rotation about the y-axis, which is the up vector. In the same way, moving the mouse vertically results in the camera tilting around its x-axis. We also clamped the amount of camera tilt between almost straight up and almost straight down. This spherical vector is the same as using Euler angles, and therefore we can convert it to quaternion representation and finally set it as the new rotation for the camera. I discussed the math behind rotations and quaternions in this video, so please feel free to watch it if you need a refresher. Running the application, I can now hold down the left mouse button and drag the mouse to turn the camera in any direction. Although we achieved our objective, I think we can improve the camera movement quite a bit. As you can see, the movement is rough and not pretty to watch. We can make the camera rotate smoothly by setting a rotation target and gradually interpolate towards the target during each frame instead of setting the rotation right away. I'll call this target the desired spherical, and I also add a Boolean member variable that's true when we need to move towards the target. The desired spherical variable is initialized in the constructor and has the same value as the spherical. When we calculate the change in orientation, we store the new value in the desired spherical instead and set move orientation to true to indicate that we need to rotate the camera. Now, instead of handling the rotation right away, we can write a function that gradually seeks the camera's desired orientation. Here we calculate the difference between the current orientation and the target orientation. If this difference is really small, that means that we reached the target and we can stop. Here we define another scale to determine how fast the current orientation will reach the target. We calculate this scale to be a function of frame time so that we get the same behavior for all frame rates. In the update function, we remember the frame time, and if we need to rotate the camera, we call camera seek function. Looks like I forgot to set the spherical value here, so let's do that. It's still not looking really smooth, that's it. Oops, wrong variable. This is better now. Great. Now let's change the camera position using keyboard. Similar to rotation, we can add 3 new member variables for current position, target position, and a boolean to indicate if the position is changing. In the update function, we check if any of the WSAD keys are pressed. This is for moving in XY direction. We can use Q and E to move the camera vertically. Using the state of these keys, we can construct a movement vector. If any component of this movement vector is non-zero, we can move the camera. I'm going to add a function to check whether two floating point values are equal. This is done by looking at the difference between the two values and checking if it's less than some small epsilon. So now if the move vector is non-zero, we need to move the camera. First, we need to initialize the position variables in the constructor like we did for the rotation. Then we rotate the movement vector so that it's aligned with the camera's direction. This way we always move in the direction where the camera is looking. We also scale the amount of movement, which determines how fast the camera moves around. The resulting vector tells us by how much the camera needs to be moved. We can add this to the desired position and turn on camera movement. In camera seek, we again calculate the difference between the current and target positions and check if we still need to move the camera. If that's the case, we partially add the difference to the position and set it as the new position for the camera. And now we can happily move around the scene using our input system. This is nice and smooth, and we can even fine-tune the camera speed and make it frame rate independent as well. I'm going to do that in the next video. We'll also add input bindings to our input system so that we don't have to check for keys in the update function every frame. As always, thank you so much for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!